Hello geoscientists. Flowers talks artificial intelligence in earth science. Welcome.
Hello, geoscientists. Let's weigh in on how best we could harness the power of artificial intelligence, AI, to enhance research in earth science and the profession. AI is a tool and has a broader application. To avoid spreading its application across a wide spectrum, we shall narrow our conversation to AI's application to the field of earth science and the profession.
I am Flowers, and we all understand the importance of staying ahead of the curve, of seizing every opportunity to elevate our knowledge and our impact. And that's precisely what we're here to talk about today. This presentation is not a course, but rather an opportunity for us to brainstorm together and progress the conversation of embracing or integrating AI into the geoscience profession. In a world where change is the only constant thing, embracing innovation technology is not just a choice, but a necessity. Today, we stand on the brink of a revolution where the integration of cutting-edge technology and timeless wisdom propels us into a new era of understanding our planet Earth. Let's talk artificial intelligence.
Artificial intelligence, or AI, is nothing new. It's been around with us for ages. However, it is trending today because it is getting better every day and practically urging us to incorporate it into our professional fields. In this respect, I would limit my contribution to our conversation by simply highlighting the importance of incorporating AI in earth science research for advancements and sustainable practices. I would also provide some fundamental distinction between AI and machine learning in order to help narrow the conversation to our interest in incorporating AI in all things geoscience. Now, let's dive into the fundamental insights. What is the fundamental difference between machine learning and artificial intelligence? Let us imagine you have a really smart robot. Now, this robot can do lots of cool stuff, such as understand what you say, learn new things, and even make decisions on its own. It can also translate text into voice. Let's ask your robot a question. Hi, robot. Are you a smart robot?
Yes, I am a smart robot and can sound human.
Machine learning gives your smart robot the ability to learn from its experiences. It's like teaching it to recognize patterns and make predictions based on what it's learned before. On the other hand, artificial intelligence, or AI, is like the big idea behind making the robot smart in the first place. It's all about creating machines or programs that can think and act like humans. So AI is like the brain power that helps the robot understand, learn, and make smart decisions. In simple terms, machine learning is one way we make robots smart. And artificial intelligence is the big idea behind making the robots smart in the first place. So, our collective question is, how do we harness the power of AI in shaping the future of earth science research and the profession? Imagine you're studying certain rocks and trying to understand how they form and change over time. In this case, machine learning would be like using computer algorithms to analyze huge amounts of data about rocks. These algorithms can spot patterns and make predictions about things like the formation of certain rock types or the likelihood of earthquakes based on a past seismic activity. In our field, AI might help us develop models that simulate how different geological processes work or predict environmental changes based on various factors like climate data, soil composition, and human activity. So while machine learning is a specific technique we use to analyze data and make predictions in earth science or geoscience, artificial intelligence, on the other hand, encompasses a broader range of techniques and goals aimed at creating computer systems, the brain, that can think and learn like humans, potentially understand and interact with the Earth's systems. Now that we have an appreciation of the power of AI, how do we harness the power of AI in shaping the future of earth science research and the profession? This is our biggest question. Our conversation around this subject-powered question is our objective for this session. To harness the power of AI in the pursuit of unraveling the secrets held within the Earth's vast landscapes, from the depths of its oceans to the heights of its mountains. Let's envision a world where AI serves as our steadfast companion in the realm of Earth science or geoscience research. Our first objective is to leverage AI to enhance our understanding of geological phenomena such as seismic activity and volcanic eruptions. Imagine if we could predict these events with unprecedented accuracy, providing communities with the foresight needed to mitigate risks and save lives. In order to achieve this, we must empower AI to sift through vast amounts of data, extracting patterns and correlations that elude the human eye. Our second objective, therefore, will be to develop AI algorithms that are capable of processing geological data at lightning speed in order to unveil insights that would have otherwise remained hidden in the depths of complexity. But here's the beauty of it all. While the challenges we face may be daunting, the rewards are boundless. By embracing AI in earth science, we not only enhance our research capabilities but also foster a deeper connection with our planet, enriching our understanding of its intricate systems and the delicate balance upon which all life depends. So, geoscientists, let us embark on this journey together. Fueled by curiosity, driven by innovation, and guided by the unwavering belief that through collaboration and ingenuity we can unlock the mysteries of our world and pave the way for a brighter, more sustainable future. Now, let's capture what is in AI for earth science or geoscientists in 5 key objectives. Referring to the life case scenario I gave earlier, it fits our first objective, which is leveraging AI for enhanced understanding of geological phenomena. This objective emphasizes the role of AI in analyzing complex geological data to deepen our understanding of natural processes and phenomena such as earthquakes, floods, or mineralization. AI-driven analysis can uncover patterns and insights that may not be readily apparent through traditional or conventional methods. These could lead to breakthroughs in scientific understanding. The second objective is predicting natural disasters through AI-driven models and analysis. This second objective highlights the potential of AI to improve accuracy and timeliness of predictions for natural disasters, including earthquakes, floods, and landslides. By analyzing historical data, environmental factors, real-time sensor data, AI models can forecast the likelihood and impact of such events, enabling proactive measures to be taken to mitigate risks and protect lives and property. The third objective is optimizing resource management in earth science with AI. This third objective focuses on how AI can optimize the management of natural resources, including minerals, water, and land, through data-driven decision-making and predictive analytics. AI-driven optimization algorithms can help maximize resource extraction efficiency and minimize environmental impacts to inform sustainable development practices in the field of earth science. Number 4, tracking and combating illegal mining activities. This objective addresses the pressing issue of illegal mining and its detrimental impacts on the environment, communities, and the economies. AI technologies such as satellite imagery and data analytics can be leveraged to monitor and detect illegal mining activities. This will enable or empower the authorities to take timely enforcement actions and implement targeted interventions to curb the practice. The fifth objective is centered on informing evidence-based policy formulation through AI insights. This objective underscores the importance of using AI-driven insights to inform evidence-based policy formulation and decision-making in earth science. By analyzing vast amounts of data and generating actionable insights, AI can provide policymakers with valuable information to develop effective regulations, allocate resources, and address pressing challenges facing the field. Now, let's look at a few case scenarios in order to expand the objectives. So I will describe real-life case scenarios, including the Bagre Dam overflow, Akosombo Dam spillage, and historical seismic events in Ghana. I will use this in order to highlight the potential of AI to enhance monitoring, prediction, and response efforts in such scenarios. The Bagre Dam overflow in Ghana caused devastating floods, which resulted in loss of lives, destruction of infrastructure, and displacement of communities. This is a tragic reminder of the immense power and unpredictability of nature, especially in regions prone to such occurrences. In such situations, AI can play a crucial role in both prediction and response. By analyzing various data sources such as weather patterns, water levels, soil moisture, and satellite imagery, AI models can provide early warnings of potential flooding events. These warnings can then be disseminated to communities in at-risk areas, allowing them enough time to evacuate and take necessary precautions to minimize the impact of the disaster. Furthermore, AI can aid in post-disaster assessment and recovery efforts. By analyzing satellite imagery and other data sources, AI algorithms can quickly assess the extent of damage, identify areas in need of assistance, and prioritize resource allocation for efficient relief efforts. The Bagre Dam overflow serves as a sobering reminder of the importance of proactive measures and the potential of AI to mitigate the impact of natural disasters or man-made or man-influenced disasters. By leveraging technology and collaboration, we can work towards building more resilient communities and reducing the human cost of such events in the future. The Akosombo Dam spillage in Ghana is another significant event in the country's history, demonstrating a critical need for effective management of water resources and infrastructure. The Akosombo Dam, located in the Volta River, plays a vital role in Ghana's energy production and water supply. When heavy rainfall occurs, these can cause the water levels to rise rapidly, and such was the case during the spillage events. This can lead to overflowing and subsequent flooding downstream. Just like with the case of the Bagre Dam overflow, AI can contribute to both prediction and response efforts in the event of a spillage. By monitoring various environmental factors such as rainfall patterns, water levels, and dam operations data, AI models can provide early warnings of potential spillage events. This will allow authorities to take preemptive measures to mitigate the impact. Additionally, AI-powered decision support systems can help optimize dam operations. This will ensure that water levels are managed efficiently to minimize the risk of overflow while maximizing energy production and water supply. In the aftermath of a spillage, AI can assist in assessing the extent of flooding, identifying affected areas, and coordinating rescue and relief efforts. By integrating AI into emergency relief protocols, the authorities can improve their ability to manage crises effectively and minimize the impact on affected communities. The Akosombo Dam spillage serves as a reminder of the complex challenges associated with managing water resources and the potential of AI to enhance our ability to address these challenges proactively. Through continued investment in technology and collaboration, we can work together towards building more resilient infrastructure and safeguarding communities against the devastating effects of natural disasters. Now let's look at historical seismic activities. Monitoring and predicting seismic activity, as well as implementing measures to mitigate the risk and enhance building resilience, are essential components of disaster management efforts. This will translate into minimizing the impact on communities and infrastructure. Preparedness for seismic activity in several ways. These include 1. Early warning systems. AI can analyze real-time data from seismic sensors, satellite imagery, and other resources to detect precursors to earthquakes and provide early warning alerts. By leveraging machine learning techniques, these systems can improve the accuracy and timeliness of earthquake predictions, giving authorities and residents valuable time to prepare and take preventive measures. A second way is risk assessment and vulnerability mapping. AI-powered risk assessment models can analyze geological, geospatial, and socioeconomic data to identify areas prone to seismic hazards and assess the vulnerability of buildings, infrastructure, and communities. By mapping high-risk areas and prioritizing mitigation efforts, the authorities can allocate resources more effectively and reduce the potential impact of seismic activities. Thirdly, infrastructure resilience planning. AI can assist in designing and retrofitting buildings and infrastructure to withstand seismic forces. Advanced modeling can simulate earthquake scenarios and assess the structural integrity of buildings, bridges, and other critical infrastructure components. AI-driven optimization algorithms can then recommend design modifications to enhance resilience and minimize damage in the event of an earthquake. Fourth is public awareness and education. AI-powered communication tools can disseminate information about earthquake risk, preparedness measures, and evacuation procedures to the public. For example, chatbots, mobile apps, interactive platforms can be used to deliver personalized recommendations and real-time updates. This will empower residents to make informed decisions and take proactive steps to protect themselves and their communities. The fifth way is post-disaster response and recovery. AI technologies such as computer vision and natural language processing can analyze satellite imagery, social media data, and aerial surveys to assess damage and prioritize response efforts in the aftermath of an earthquake, for example. AI-driven decision support systems can also assist emergency responders in coordinating rescue operations, distributing aid, and restoring essential services to affected areas more efficiently. Investing in AI-driven technologies and initiatives can help the country build a more resilient future and mitigate the potential impact of natural disasters on its community and economy. In looking into AI systems for earth science, the question we must answer is, how does AI stand out in comparison to humans analyzing statistical data in order to inform decision on monitoring and predicting disasters, research paradigms, and other related geo-events? AI algorithms can process vast amounts of data at incredible speeds, far surpassing the capabilities of humans. This allows for real-time analysis of data streams from various sources, which will enable rapid detection of patterns and anomalies that may indicate impending floods, or seismic events. For example, AI excels at detecting complex patterns and correlations within large datasets, even those that may not be readily apparent to human analysts. An AI model can easily assess complex data that are beyond human capabilities. In this sense, by leveraging advanced machine learning techniques, AI can identify subtle signals and trends that may precede natural disasters. This will provide early warning alerts that humans may overlook. AI, or AI systems to be precise, can scale effortlessly to handle massive volumes of data from multiple sources simultaneously. This is a property of scalability. AI's capacity to be scalable allows for comprehensive monitoring of vast geographic areas and diverse environmental conditions. This will ensure that no potential threat goes unnoticed. Another property of AI is that the AI algorithms can continuously adapt and improve over time through the process of machine learning. By analyzing historical data, that is past experience, and incorporating feedback from real-world events, AI models can refine their predictive capabilities and become increasingly accurate in forecasting floods or seismic events. Another component of AI systems is that AI operates based on predefined algorithms and rules. These lead to more consistent and objective analysis compared to human judgment, which may be influenced by biases or subjective interpretations. Last but not least, resources can be optimized by automating data analysis tasks. AI frees up human resources to focus on higher level decision making and response efforts. This allows for more efficient allocation of personnel and resources during emergency situations, which will improve overall disaster preparedness and response. We've talked about AI systems for earth science. Now, let's use this time period to be specific about some of the AI systems that can be used in earth science research and the profession. So I will cite at least 6 examples. The first one is machine learning models. Machine learning algorithms, which includes supervised, unsupervised, and reinforcement learning techniques, can be trained on historical data to identify patterns and correlations related to natural disasters. By historical data, we mean past records. These models can then be used to make predictions and generate early warning alerts based on real-time data inputs. The second AI system is neural networks. Neural networks is a subset of machine learning algorithms which is inspired by the structure of the human brain. These structures, called neural networks, are particularly well suited for tasks involving complex patterns and nonlinear relationships. As such, this ability makes it easier for neural networks to be applied to various aspects of disaster prediction, such as image recognition in satellite imagery analysis or time series forecasting of environmental data. The third AI system is deep learning. Deep learning is also a subset of machine learning. It uses neural networks with multiple layers. It has shown to be remarkable in successfully handling large and unstructured data sets. Deep learning models can be used for tasks such as image recognition, natural language processing, and sensor data analysis, all of which are relevant to monitoring and predicting natural disasters. The fourth system is expert systems. Expert systems are AI systems that leverage domain-specific knowledge and rules to emulate human expertise in a particular field. In the context of natural disaster prediction, for example, expert systems can integrate knowledge from domain experts, scientific research, and historical data to make informed decisions and generate recommendations for response actions. The fifth AI system is geospatial analysis. Geospatial analysis involves the processing and interpretation of spatial data, such as satellite imagery, geographic information system, which is GIS data, and remote sensing. AI techniques, including machine learning and deep learning, can be applied to geospatial data for tasks such as land cover classification, change detection, and anomaly detection, which are essential for monitoring and predicting natural disasters. The last but not the least is data fusion systems. Data fusion systems integrate information from multiple sources and sensors to provide a more comprehensive understanding of environmental conditions and potential disaster risks. AI techniques such as Bayesian networks and ensemble learning can be used to fuse heterogeneous data streams and improve the accuracy and reliability of disaster prediction. So in sum, by leveraging these AI systems, these 6 AI systems and techniques, researchers, practitioners or consultants, or in general, geoscientists, can develop robust and effective solutions for monitoring and predicting natural disasters, which will ultimately enhance our ability to mitigate risks and protect vulnerable communities. Now, in this session, let's discuss how AI can revolutionize mineral exploration in Ghana. We shall highlight the applications of AI in data analysis, predictive modeling, remote sensing, and ecological restoration planning within this context of mineral exploration. So yes, apart from using AI to optimize monitoring and prediction of seismic, flood activities, and other naturally occurring disasters, we shall delve into AI's applications to mineral exploration in the mining sector in Ghana, which is applicable to the same field elsewhere. So I will apportion these into 6 topics. The first segment is data analysis and target identification. AI or AI algorithms can analyze vast amounts of geological, geophysical, and geochemical data to identify prospective areas for mineral exploration. By integrating data from various sources, including satellite imagery, airborne surveys, and geological mappings, AI models can pinpoint potential mineral deposits with greater precision. This will reduce the need for extensive field work and exploration drilling. The second system is predictive modeling. AI-driven predictive models can assess geological and environmental factors associated with mineralization, such as rock composition, structural features, and hydrothermal alteration patterns. These models can then generate probabilistic maps and predictive analytics to prioritize exploration targets based on their likelihood of containing economically viable mineral deposits. 3. Remote sensing and image analysis. AI techniques such as computer vision and machine learning can analyze satellite and drone imagery to detect subtle geological features and anomalies indicative of mineralization. By automatically processing and interpreting large-scale image datasets, AI algorithms can accelerate the identification of exploration targets and reduce the reliance on manual interpretation by geologists, for example. The fourth property is geological mapping and 3D modeling. AI can assist in creating detailed geological maps and 3D models of prospective mining areas using data from various sources. These include geological surveys, drill core samples, and geophysical surveys. By automating the mapping process and integrating multi-dimensional datasets, AI technologies can provide geologists with valuable insights into the subsurface geology and potential mineralization patterns. The fifth element is targeted drill campaigns. AI-driven optimization algorithms can optimize drill hole planning and target selection to maximize the chances of discovering mineral deposits while minimizing exploration costs. By analyzing geological data and historical drilling results, AI models can recommend optimal drill hole locations and trajectories to efficiently test exploration targets and validate mineralization hypotheses. Last but not the least is environmental impact assessment. AI can facilitate environmental impact assessments by analyzing geospatial data and predicting the potential environment effects of mining activities. AI-powered models can simulate the impacts of mining operations on ecosystems, water resources, and air quality. These will help mining companies to develop sustainable mining practices and mitigate environmental risks. So, in addition to the previous systems we talk about, we can add that by leveraging AI technologies in mineral exploration, the mining sector in Ghana or elsewhere can streamline the exploration process, accelerate discoveries, and optimize resource management practices. This can lead to more efficient utilization of Ghana's mineral resources, sustainable economic development, and enhanced environmental stewardship in the mining industry. I thank you very much for being generous with your time.
Hi, Geoscientists. You've been wonderful audience. And thanks to Flowers.